What if I told you that every modern aircraft, Formula One car, gas turbine, and wind turbine has been designed using mathematical models that engineers know are not exact? Even with the world's fastest supercomputers, we still cannot perfectly predict turbulent flow. Why? Is the turbulence simply too complicated? Or is there something fundamentally impossible about the mathematics itself? Today, we'll uncover why turbulence remains one of the greatest unsolved challenges in engineering, physics, and mathematics, and why every turbulence model, from RANS to LES to DNS, is really a carefully chosen compromise. Turbulence is everywhere. It determines the lift generated by aircraft, the drag experienced by automobiles, the efficiency of turbines, the cooling of electronics, even the prediction of weather and climate. Understanding turbulence isn't just an academic exercise, it influences fuel consumption, emissions, safety, renewable energy, and billions of dollars in engineering decisions every year. Yet, despite more than a century of research, we still don't possess an exact universal description of the turbulent motion. Let's begin with a simple question. What is turbulence? Imagine fluid flowing smoothly through a pipe. Every particle follows a predictable path. This is laminar flow. Now gradually increase the Reynolds number. Small disturbances begin to amplify. The orderly motion loses stability. Large vortices appear. These vortices break into smaller vortices. Those smaller vortices create even smaller ones. Eventually, the flow becomes chaotic. This is turbulence. Not random, not disordered, but extraordinarily complex. Here's the real challenge. Turbulence isn't made of one vortex, it's made of millions. Large eddies transfer energy to smaller eddies. Those smaller eddies generate even smaller structures. Eventually, the smallest motions become so tiny that the viscosity converts their kinetic energy into heat. This continuous transfer of energy is known as the turbulent energy cascade. The problem is that every scale interacts with every other scale. To predict turbulence perfectly, you would need to resolve all simultaneously. All fluid motion is governed by one remarkable set of equations, the Navier-Stokes equations. These equations describe the conservation of mass and momentum. In principle, they contain every detail of turbulent motion, but there's a problem. For realistic engineering flows, turbulence spans an enormous range of length and time scales. Solving these equations directly for every scale quickly becomes computationally impractical. This is why engineers turn to turbulence models. In 1895, Osborne Reynolds proposed a revolutionary idea. Instead of solving every tiny fluctuation, why not separate the flow into an average component and a fluctuating component? This simple decomposition transformed turbulence research, but it also created a new problem. When we average the Navier-Stokes equations, new unknown terms suddenly appear. These are the Reynolds stresses, and they represent the influence of turbulence on the mean flow. Unfortunately, the equations for these new quantities introduce even more unknowns. This is known as the closure problem. The closure problem is the reason turbulence modeling exists. Reynolds average Navier-Stokes or RANS addresses the closure problem by modeling the Reynolds stresses. Rather than resolving every turbulent motion, RANS predicts their average effect. The reward is extraordinary computational efficiency. A simulation that would take months with DNS can often be completed in hours. This is why RANS remains the workhorse of industrial CFD, but averaging also removes much of the instantaneous turbulent structure. The fine details are sacrificed for speed. Large eddy simulation takes a different approach. Instead of averaging everything, LES directly resolves the large energy containing vortices. Only the smallest turbulent motions are modeled. This produces dramatically richer flow physics, separated wakes, coherent vortices, transient structures. But there is a price. Computational cost rises rapidly, especially near walls where the smallest turbulent scales become extremely difficult to resolve. Direct numerical simulation represents the closest thing we have to the exact numerical solution of the Navier-Stokes equations. No turbulence model. Every relevant turbulence scale is resolved. DNS provides extraordinary insight into turbulence physics, but its computational cost increases dramatically with Reynolds number. For most practical engineering applications, DNS remains beyond today's computational capabilities. Artificial intelligence is changing computational engineering. Neural operators, physics informed neural networks, surrogate models, reduced order models. These techniques can accelerate prediction and reduce computational cost. But AI is not replacing physics. It learns patterns from existing data. Its reliability still depends on the quality of the governing equations, training data, and validation. AI is becoming a powerful new tool, but not a substitute for fundamental fluid mechanics. So, can we solve turbulence perfectly? Not for the engineering problems we face today. Instead, engineers rely on validated approximations that balance accuracy with computational cost. RANS, alias DNS, each represents a different point on the spectrum. Understanding these methods isn't just about choosing a solver, it's about understanding the assumptions behind every simulation you run. The remarkable achievement of modern engineering isn't that we have eliminated uncertainty, it's that we have learned how to design safe, efficient, and reliable systems despite it. In this video, we have explored why turbulence remains one of the greatest challenges in computational engineering, but we have only scratched the surface. In the next episode, we will dive into the closure problem itself, how Reynolds stresses arise, why they make the equations unsolvable without modeling, and how turbulence models attempt to close the system. If you want to master CFD from first principles to modern AI, subscribe to PRISM CFD.ai and join us on this journey through the science of fluid motion.